This is a hands-on class, so open the lab guide and deploy alongside me. Last class we got up close with the pod, and we ended on its most important property. A pod is ephemeral. It is disposable, and when it dies, it stays dead. And A2112, nothing brings a bare pod back on its own. We said at the time that you almost never run bare pods in production, and that something has to manage them for you. Today, we meet that something, and it is the object you will use to run essentially every real workload on Kubernetes, the deployment. A deployment is a controller that owns your pods and keeps them running exactly the way you want. You tell it declaratively, N82020, I want this many copies of this pod running, and 82021, and the deployment makes that true and keeps it true, and 82012 forever automatically. If a pod dies, the deployment replaces it. If you want more capacity, the deployment scales up. If you want to ship a new version of your app, the deployment rolls it out without any downtime. And if that version turns out to be broken, the deployment rolls it back. This is where Kubernetes truly delivers on its promise of resilient, self-healing, easily updated applications. Today, you will learn what a deployment is, how it heals and scales, and how it updates and rolls back. Let us run some pods properly. Here is our path for today. First, why deployments exist. Second, what a deployment actually is. Third, self-healing. Fourth, scaling. Fifth, rolling updates. And sixth, rollback. Let us dive in. Let us start with why deployments exist at all, because the reason follows directly from last class. We established that pods are ephemeral. A bare pod, an AT-AT wall, one you create directly, an AT-AT wall, has no self-healing whatsoever. If its node fails, if it crashes, if it is evicted, it simply dies and stays dead. Your application is just gone, with nothing to bring it back. For anything you actually care about keeping alive, that is unacceptable. Running naked pods in production would mean your app disappears the first time any little thing goes wrong. So you need something sitting above the pod that watches it and keeps it running an 80-100 fall. Something that notices when a pod has died and creates a replacement, that maintains the number of copies you want, that handles updates gracefully. That N80-200-200, something N80-200-200 is a controller. And for running stateless applications, N80-200-200, which is the vast majority of workloads, N80-200-200, the controller you use, is the deployment. It is the manager that turns fragile, disposable pods into a reliable, durable service. This is the object model from earlier coming to life exactly as designed. You do not manage mortal individual pods by hand. You declare a desired state to a controller, and the controller relentlessly reconciles reality toward it. The deployment is the most important, most used example of that pattern. From here on, when you run application on Kubernetes, you will almost always do it through a deployment, and the bare pods from last class become just a teaching tool and AT-HODUL, the atoms that the deployment now manages on your behalf. Understanding the deployment is understanding how real applications actually run on Kubernetes. So the takeaway, bare pods are ephemeral with no self-healing, so they die and stay dead, which is unacceptable. For real applications, NA2112, you need a controller above them. And for stateless workloads, that is the deployment, the manager that turns disposable pods into a reliable service by reconciling reality toward your declared desired state. Now let us define exactly what a deployment is and does, because it is beautifully simple at heart. A deployment is an object where you declare a desired state for your pods and AT-42 and the central part of that is how many replicas you want. You say, in effect, NAT2020, I want 3 copies of this particular pod running at all times. NAT21, you specify the pod, NAT2020, its container image, its configuration NAT2020, and the number of identical copies, the replicas, you want running. That declaration is the whole intent, this many of this pod, always up. What the deployment then does is continuously maintain that desired count. The cluster constantly compares the number of pods actually running against the number you asked for and works to make them equal. If you ask for 3 and 3 are running, it does nothing and A2112, all is well. If the actual number ever drifts away from the desired number, the deployment acts to correct it, bringing reality back in line. It is a tireless caretaker whose single obsession is NA220. Keep exactly the requested number of these pods alive. NAA221. This is the spec versus status idea, made concrete and powerful. The replica count you declare is the spec and A212 what you want. The pods actually running are the status and A21 what is. And the deployment N39's entire job is to close any gap between them forever. Everything else a deployment does and ATA21. Healing, scaling, updating, and ATA01 is really just this one principle applied in different situations. Always keep the running pods matching the desired specification. Once you see that a deployment is fundamentally a machine for maintaining a desired count of pods, all of its behaviors become obvious consequences of that single, relentless goal. So the takeaway, a deployment is an object where you declare a desired state, an A2112, chiefly how many replicas of a pod you want, an A2112, and it continuously compares the actual number of running pods against that desired count and acts to keep them equal. It is a tireless caretaker, closing the gap between the spec you want and the status that is, forever. The first and most vital behavior that falls out of maintaining a desired count is self-healing, and it is genuinely a little magical to watch. Picture a deployment maintaining 3 replicas, and one of those pods suddenly dies and A25212. Its node crashes, or the container fails. In that instant, the actual number of running pods drops to 2, while the desired number is still 3. There is now a gap between what you want and what exists. The deployment notices this gap almost immediately, because it is constantly comparing actual to desired. Seeing that actual has fallen below desired, it does the obvious thing. It creates a brand new pod to replace the one that died, bringing the running count back up to 3. It does this entirely on its own in seconds, with no human involvement whatsoever. The failure is detected and repaired automatically, and your application is back to full strength before anyone would even notice. This is self-healing, and it is one of the headline features of Kubernetes. It means individual pod failures and 80/100 which, remember, are constant and expected at scale and 80/100 simply do not matter to your application and uptime. Availability. A pod dies, the deployment replaces it, the service carries on. You will see this vividly in today NTI's lab. You will create a deployment, then manually delete one of its pods, and watch Kubernetes immediately spin up a replacement to restore the count right before your eyes. That moment and A212 kill a pod and seed instantly come back and A212 is when the power of the whole system really lands. The disposability of pods, which sounded like a weakness 2 classes ago, becomes a strength precisely because the deployment turns it into automatic recovery. So the takeaway, self-healing falls directly out of maintaining a desired count and A212. When a pod dies, the actual count drops below desired. The deployment notices the gap and creates a replacement automatically in seconds, so constant. Expected pod failures simply do not affect your application and 39's availability, kill a pod and watch it come right back. The same desired count machinery gives you another superpower almost for free: effortless scaling. Scaling means changing how many copies of your application are running, and with the deployment, it is astonishingly simple. You just change one number and A212, the replica count. Change the desired replicas from 3 to 10, and the deployment sees that actual 3 is now below desired 10, and it creates 7 more pods to reach the new target. Change it from 10 back down to 3, and it removes 7 pods to match. Scaling up and scaling down are both just the deployment doing its one job and A212, keeping actual equal to desired and A212 against a number you changed. In practice, this is a single command or a one-line edit to your deployment. There is no complicated procedure to add capacity. You state the new desired count, and the cluster makes it happen, spreading the new pods across your nodes. This is what makes Kubernetes so powerful for handling variable load. Traffic surging for a big event, scale your deployment up to handle it. Quiet overnight, scale it back down to save resources. The elasticity you learned about in cloud fundamentals becomes, on Kubernetes, as easy as changing a replica count. And because scaling is just adjusting the desired number, it composes perfectly with self-healing and AT112. They're the same mechanism. Whether a pod count is wrong because one died or because you changed the target, the deployment responds identically, bring actual back to desired. This unity is the elegance of the design. One simple idea and A2012 maintain the declared number of pods, and A2012 simultaneously gives you automatic recovery from failure and effortless scaling to any size, up or down, on demand. That is a remarkable amount of power from a single, clear principle. So the takeaway, scaling with the deployment, is just changing the replica count and A200 pods. Raise it and it creates more pods. Lower it and it removes some any A200 fall, making it a one-command way to handle variable load up or down. And because it is the same desired count machinery as self-healing, one simple principle delivers both automatic recovery and effortless elasticity. Deployments do not just keep your app running any 82 towel for, they also handle the delicate task of updating it to a new version without ever taking it down. This is the rolling update. Think about the challenge of shipping a new version of your application. The naive approach and A212 stop all the old pods, then start all the new ones and A21s means there is a window where nothing is running and your service is down. For anything users depend on, that downtime is unacceptable. You want to move from the old version to the new version while continuously serving traffic with no gap. That is exactly what a rolling update does. Instead of replacing everything at once, the deployment replaces pods gradually, a few at a time. It starts a pod on the new version, waits until it is up and healthy, then removes one old pod and A212 and repeats, rolling through the fleet piece by piece. At every moment during the update, there are healthy pods serving requests, a mix of old and new, but never a moment where nothing is available. The old version is phased out and the new one phased in smoothly, while the application stays fully up the entire time. This is how you achieve zero downtime deployments, and it is a huge deal. It means you can ship updates as often as you like, and 82 fall multiple times a day if you want an 82 fall without ever interrupting your users. The deployment manages the whole careful choreography for you. The gradual replacement, the health checks between steps, the pacing. You simply tell it to use the new version and A212, change the image in the deployment and A212, and it performs the rolling update automatically. What was once a stressful, downtime-inducing event becomes a routine, invisible background operation. This safe, continuous updating is one of the biggest reasons teams adopt Kubernetes in the first place. So the takeaway, a rolling update ships a new version by replacing pods gradually and at a 202 fall, starting a new pod, waiting until it is healthy, then removing an old one and repeating an RR2 fall. So there are always healthy pods serving and the application stays fully up throughout, giving you zero downtime deployments. You can perform as often as you like just by changing the image. Updates sometimes go wrong, and A212. The new version has a bug that only shows up in production. Deployments have you covered here too, with Rollback. Despite your best testing, a new version you roll out can turn out to be broken in ways you did not catch until real traffic hit it. Now, you have a bad version live in production, causing errors, and you need to get back to safety fast. The pressure in that moment is real, and doing it by hand and A212, scrambling to redeploy the old version and A212, is exactly when mistakes get made. This is precisely the situation Rollback is built for. A deployment keeps a history of its rollouts and A212. It remembers the previous versions it was running. So when a new release goes wrong, recovering is a single command, rollback. the deployment simply performs a rolling update in reverse, back to the previous known good version, using the same safe, gradual, zero downtime mechanism. Within moments and with no downtime, your application is restored to the version that worked, while you calmly investigate what went wrong with the new one. A potential crisis becomes a quick, controlled, one-command recovery. This is the safety net that makes frequent updating psychologically and practically safe. Because you know that any bad release can be undone instantly and cleanly, you can ship changes with confidence rather than dread. The combination is powerful. Rolling updates let you deploy new versions with zero downtime, and rollback lets you undo a bad one just as smoothly. Together, they turn deployment and 81.12v historically one of the scariest, most failure-prone parts of running software, and 81.12v into a routine, low-risk, reversible operation. That confidence to change things safely and to recover instantly when something slips through is exactly what good engineering infrastructure should give you, and the deployment delivers it. So the takeaway? A deployment remembers its rollout history. So if a new version is broken in production, one rollback command performs a reverse rolling update to the previous known good version with no downtime and 82.112, turning a potential crisis into a quick, controlled recovery and making frequent updates safe, because any bad release can be undone instantly. Let us connect all of this to what you will actually type, since this is a hands-on class, and these commands are ones you will use constantly. You create a deployment declaratively, the way you learned in the object model class. Write a YAML manifest specifying the pod and the replica count, and apply it. Or, for quick work and learning, create one imperatively with a single command. Either way, the moment it exists, the deployment starts doing its job and 82.12, launching your pods and maintaining the count. And you inspect it just like anything else. Get to see it and its replicas, described for detail and events. To scale, you either edit the replica count in the manifest and reapply, or run a scale command with the new number and 82.12, and watch the pod count change to match. To update, you change the image the deployment uses and 82.4 again by editing and applying, or with the command and 82.4, and the rolling update begins automatically. You can watch its progress with the rollout status command, which shows you the update proceeding step by step until it completes. These few verbs and 81.12, apply, scale, and rollout and 81.12 are the core of daily Kubernetes work. And when something goes wrong, the rollout command is also your rescue. Rollout undo returns the deployment to its previous version, performing that safe reverse rolling update. So the complete toolkit is small and memorable. Create or apply to launch it, scale to resize it, rollout status to watch an update, and rollout undo to reverse a bad one. In today in IN. Sign S Lab. You will do all of these. NIN 8012 create a deployment, delete a pod and watch it heal, scale it up and down, roll out a new image, and roll it back. Doing each one yourself is what turns these concepts into genuine, confident skill. Master this handful of commands and you can run real applications on Kubernetes. So the takeaway, the daily deployment toolkit is small and 80/80/12. Apply or create to launch it, scale to change the replica count, rollout status to watch an update proceed, and rollout undo to reverse a bad release and 8200 and today an 80 site and 80 sign DI and 8200 creating a deployment and watching it heal, scale, update, and roll back, which turns the concepts into real skill. Before we recap, let us note a few habits that make working with deployments smooth and safe. Tying today, INST9 S ideas to good practice. First, always run real workloads through deployment, not as bare pods. This is the core lesson. Bare pods are for learning and quick experiments only, because they do not heal. Anything you want to stay up and 82 any service, any application and 82 belongs in a deployment so that it gets self-healing, scaling, and safe updates for free. Make an A2I2. Wrap it in a deployment an A2I21, your default for everything real. Second, Keep your deployment defined in a version-controlled manifest and change it by editing and applying that manifest rather than by ad hoc imperative commands. This is the declarative discipline from the object model class. Your manifest is the single source of truth for the desired state and A2012, the image, the replica count, and A2020. So scaling and updating become tracked, reviewable changes to a file in JIT that gives you a clear history of what your application should be and makes rolling back a configuration change as easy as reverting a commit. And third, watch your rollouts and know your rollback. When you ship a new version, actually watch the rollout status complete and keep an eye on the new pods in 39 health before considering the update done. And remember that rollout undo is always there. If the new version misbehaves and A212, knowing you can recover instantly lets you deploy with confidence. Wrap everything real in a deployment, manage it declaratively through version control, and update with your eyes open and rollback ready. These habits make Kubernetes deployments reliable and calm rather than risky. They are how professionals run applications on this platform every day. So the takeaway, 3 habits make deployments safe and AT12 run every real workload through a deployment rather than bare pods so it self-heals. Keep the deployment in a version-controlled manifest and change it declaratively so scaling and updates are tracked and reversible. And watch your rollouts while keeping rollback ready so you deploy with confidence. Let us gather the whole class in one breath. Deployments exist because bare pods are ephemeral and do not heal themselves. A deployment holds a desired count of pods and continuously keeps reality matching it. Self-healing and AT12 when a pod dies, the deployment recreates it automatically back to the desired count. Scaling and AT2pol change the replica count and pods are added or removed to match. Rolling updates replace pods gradually so the app stays up with 0 downtime. And rollback returns a broken release to the previous working version with one command. Next class and 8.1.12.5 services, giving your pods a stable address to be reached at, one idea at a time. That is the deployment and